Bohmian mechanics, also known as pilot wave theory, was first developed by Max Born and Louis de Broglie in 1927 under the name of pilot wave theory. However, they were convinced by Wolfgang Pauli that the theory was incorrect and subsequently stopped their research in favour of the Copenhagen interpretation. Years later, in 1952, David Bohm furthered the theory and it became known as Bohmian mechanics. Bohmian mechanics is an interpretation of quantum mechanics that separates particles from the wave function by saying that particles are real entities that have well-defined positions at all times. This is known as realism. This type of interpretation is called a hidden variable theory, and all that means is that there is additional information about a system that is not contained in the wave function. The hidden variable in Bohmian mechanics is actually just the position of a particle. So a system is described by a wave function and a configuration which consists of the positions of the particles in a system. One benefit of this is that it removes the measurement problem that some other interpretations have, since taking a measurement simply involves interacting with the physical particle, with no need for a true wave function collapse. There is, however, an effective wave collapse. Since the particle has a defined position, it will exist only in one branch of the wave function. Once a measurement takes place, this position is known, and the other branches can be neglected since they no longer affect the particle. This is called an effective collapse. But if the wave function no longer defines the position of the particles, how do we find their time evolution? Well, to explain this, Bohmian mechanics says that particles experience a force from a quantum potential, which is an extra term that's added to the Schrödinger equation. This force pushes particles towards areas of large wave function amplitude, so there is a higher probability of finding particles there. The motion that results from this force is described by the guiding equation, which is a second equation that Bohmian mechanics must introduce alongside the Schrödinger equation. The guiding equation is expressed in terms of the wave function and the position of all particles in the system, but this means that a change in the position of one particle can have an instantaneous effect on the other particles, i.e., Bohmian mechanics is explicitly non-local. So if Bohmian mechanics has particles with well-defined positions on well-defined paths, how can it explain the random variance we observe in measurements? Well, it simply states that the uncertainty in a measurement comes from ignorance of the particle's exact starting position, rather than some innate randomness. This means that each individual measurement will find a result that was well defined before measuring, but a series of measurements will give a spread of results around the expectancy due to the different starting positions. The double-slit experiment is an example that can be counterintuitive in other interpretations. However, Bohmian mechanics explains this very naturally. The electron is a particle, so has a definite position at all times, meaning it takes a clear path from source to target, and always passes through only one slit. The wave function is a wave, so it passes through both slits, causing an interference pattern, which pushes the electron into interference bands. However, in order to determine which slit the electron went through, the wave function must be interacted with, and this disrupts the interference pattern and results in two clumps of electrons at the target. So if Bohmian mechanics can explain our observations while preserving realism and determinism, why isn't it more widely accepted? Well, there are a few problems with it. First of all, the explicit non-locality of the theory makes it difficult to reconcile with relativity, and so far it cannot make predictions involving it in the way that quantum field theory can. Secondly, many scientists find the inclusion of the guiding equation unnecessary. Other interpretations can make the same predictions using only the Schrödinger equation, so why overcomplicate the theory? To recap the key points of this video, Bohmian mechanics is a formulation where the wave function and particles are separate entities. Particles exist and have well-defined positions at all times. This preserves realism and determinism, but at the cost of being non-local. Particles experience a force from a quantum potential, and the resulting motion is described by the guiding equation. Uncertainty in measurements comes from ignorance of the particle's exact starting position. If you enjoyed the video, make sure to like and subscribe, and thanks for watching from the whole team.